Welcome to this OST2 course about the Enhanced System API of the TPM2 software stack, or called for short TPM2 TSS. When using the TPM software stack to talk to the TPM, we're sending TSS API calls, and then the TPM software stack translates those to TPM commands sent over the TPM command transmission interface, or TCTI for short. Usually this is hidden from the developer, and that's okay. That's the purpose of the TSS, to handle some of that communication and to create a useful abstraction for us. So the TSS still needs to send these commands to the actual TPM, and depending what the TPM is and what is our operating system, in the Linux world this is handled by the kernel driver when we have a physical TPM, and there is a TPM driver loaded, and it talks then to a physical layer, usually SPI or I2C, and this way from our application through the TSS, through the TPM driver, all the way to the physical layer, reaches the TPM, and then in the back direction we get our command response. Now in the Windows world that's handled by the TPM base service, and in a bare metal situation we are kind of responsible for our own custom input and output driver to reach the TPM. And in these situations we talk about a physical dedicated TPM. Now if you have a software TPM, which is what we do in our Docker lab environment, then we will talk to a socket, and we'll skip the TPM driver and the physical layer, and we'll talk about this more in a moment. I just wanted to cover the interesting case which we see more often, is that we have a software TPM living in a memory isolated environment, VM, or on a separate core on the same chip, also isolated in memory using hardware capabilities. Then we don't just need a TPM driver, we need some kind of inner process communication, right? To forward from our application through the TSS, reach the other world where the TPM is. Is that a VM? Is that a separate core running, let's say, with TrustZone? We still need that. So with that said, let's get closer to our situation with the lab environment. Here we have a closer overview of what the TPM2 TSS offers to us as developers, and we've taken Linux and a discrete physical TPM for this example. The TPM2 TSS provides in all cases SAPI System API, eSAPI Enhanced System API, and FAPI Feature API. Now, these three APIs have different qualities, different capabilities, and the logic of building is essentially SAPI allows you to do everything, but you have to do it by yourself. eSAPI takes away some of the manual work that you have to do, so you can do it faster and better. There's some checks on what are good values and what not when you do the TPM commands. And then in the last API, which builds on top of eSAPI, the FAPI API, then more of our freedom of choice is taken away, but at the same time we can do a lot of stuff faster and quicker with single API calls. So it depends on the granularity of how much control you want. And these APIs are available to you regardless if you want to talk to a discrete TPM or to a simulator, right? Now in this case we need a TPM driver. So regardless of which API we're using, the command will be translated essentially to TCTI, TPM command, and then will be sent to the TPM driver which lives in the kernel. From there, it will be passed on the SPI or I2C driver in the same kernel, and then it will go out to the physical layer and reach the TPM. Now, with that being said, let's look at the situation with a software TPM or a simulator. In our Docker container, we will use eSAPI, and we can do the same with SAPI and FAPI as mentioned. It doesn't matter what the TPM type is. We use eSAPI, and because we're running a TPM simulator that listens on a network socket, we don't need a TPM driver. The TPM command that the TSS will prepare based on our API call will be sent directly to the TPM simulator over the socket. So there's no physical layer, as shown here. We just directly reach the TCP socket, and from there, the simulator responds to us, and we handle that and we complete the operation. Now, because the communication happens over a socket and not using a TPM driver, we need to specify one extra argument here, instructing the TSS, and in this case this is an example with the TPM2 tools, but this needs to be set when using the API, and we will talk about this more in the next lecture, that we're going to use a simulator. On which port are we going to find that simulator? Usually, SAPI, eSAPI, and FAPI are visualized one over another, right? Because eSAPI builds on top of SAPI and FAPI builds on top of eSAPI. I do like this visualization a bit better because we also have the on the diagram the TSS2 TCTI, which handles all that communication with the TPM drivers or with the socket and so on and so on. And the TPM device driver here is actually in kernel space. The TPM access broker and source manager as well happens in kernel space. And what we need to understand here is that all of these APIs, you can use them all together. Of course, the differences between these three APIs boils down to how much of the manual work we want to do and how much control do we want to have. Now, SAPI handles the most tedious tasks for us. It is the marshalling and unmarshalling of the TPM commands, which is great. At the same time, if you want to do a real TPM application, this means more work, more APIs, including when we have to create a TPM session to protect from machine-in-the-middle attacks. Then we need to create the cryptography. We need to calculate that for the shared key that needs to be established between the TPM and our host application. So this is just one example why SAPI gives you great control, but maybe not necessarily the level of control that we need to focus on the application, on the task that we have at hand, right? Nevertheless, SAPI is great because it allows us to then move a level up. We move level up to eSAPI that is on top of SAPI, so it can use all of that marshalling and marshalling. It can use any TPM command because there is a one-to-one mapping with all of the available TPM commands. And from here on, the eSAPI also takes away some of the pain with creating the TPM sessions. And we can have that started just with an eSAPI command, and then we can establish the shared key. We can protect from machine-in-the-middle attacks. We can also do some operations with the TPM objects easier, again, because eSAPI tracks the metadata that we created. It does not mean there is a security concern here. It is more of a, for example, there is a name being calculated for your generated TPM keys. It's a digest, and eSAPI tracks that as well. So we don't have to make multiple calls to get the name. It sits in a structure in the eSAPI context. And of course, if you decide, you can free that eSAPI context and create a new one and start over. So from that perspective, eSAPI has these benefits. Now, what are the drawbacks? Well, creating a TPM policy with eSAPI naturally requires multiple commands. You need to go and look for the TPM commands. You need to call them in the right order. You need to prepare your arguments and so on and so on. Now, with FAPI, moving again a level up, that sits on top of eSAPI, we have a policy language that works in JSON. Also, we have a key store that makes the management of keys even easier, right? And again, this is a great benefit. It comes at a cost. With FAPI, we have a single API for the create primary and child keys. And while it's very convenient, I think for this course, for the intermediate TPM usage, we still need to make a very good distinction between the primary and child keys. And I would like us to keep that distinction in this course. So this is another reason using eSAPI and not FAPI. Also, using this policy definition language would be a great convenience, but we need to get down to the nitty-gritty and understand TPM2 policy, which is part of this course. We are opening that topic. We're going to learn about PCR policy and probably a few others. So this is why eSAPI, I think, is the better fit. It will allow us to do the same thing and learn more without taking away the fun and the difficulty. And that's the reason why we're here. Now, as this is the first lecture where you have labs to perform that you can see as an exercise to check what we've talked about, check what you learn. In this case, there is just a very straightforward lab where you'll be asked to download the template, the eSAPI template that we provide for you in our GitLab repo with all the code from this course and solutions. The important thing is that you run the Docker container, build the template app, and see that it works. And what it will do is actually just get you a random number, and this way, you know, okay, I'm able to talk to TPM simulator using eSAPI. You can look at the source code and you can prepare yourself for the modifications moving forward. In case you need help, please write to our OST2 discussion boards. Other students are doing the same labs. You're experiencing probably similar difficulties. Sometimes it's exactly the same issue that you're having, so you can help each other out. Also, when there's a major issue, we try to respond and address it. If there's something that needs to be fixed or something is unclear, we add more information, we add more explanations, and so on and so on. So please make sure to use the OST2 discussion boards for any questions related to this lecture. You can find the discussion box after each lecture. This helps us to understand the context of your question.